Yesterday we derived one more consequence of the band theory. We found the expression for the effective mass, if you remember. And we said that the effective mass is the mass with which electron will move in a crystal under the influence of electric field. So this is the real mass, effective mass, which will enter the Newton equation. So we can maybe go a bit further, what we announced yesterday, starting from any energy dispersion. We already derived velocity. I'm repeating every time. No. Velocity. And now we can also derive the effective mass. So we need to find one more derivative from here. And at these points, we have a maxima, extrema. It means it will be zero derivative. But however, we have, yes, I was saying something at the edges, which was wrong. I forgot with whom. It's not the edges, it's the point of inflection of the original band. Then you have 1 over infinity, 1 over 0, which gives infinity. So along these points, we will have infinite effective mass. And I think this is I think it goes like this if you do the derivation carefully. So, coming back to it. What is the meaning of the infinite effective mass? Okay, mu, let's put mu here also. Force is constant. You always have the field acting in one direction, not changed. Well, from the Newton law, yes, William?
I think if the effective mass is infinite, then at that point or in that interval it's infinite, then the electron or the electron moves with the slowest velocity.
Okay, you're very close. It's not the velocity, it's the acceleration.
Okay, yes.
Acceleration, no? Which, I mean, you can express. Could start as F over m. This is infinite, it means there is no acceleration. And
however, I have a question.
Okay, just to finish. And indeed, it's the point of inflection. Until that point, it was moving like free electron. At that point, it starts feeling the crystal metal pushing in the other direction, and these two velocities kind of become accelerations, its forces become equal, and the velocity starts changing the trend. It starts reducing at that point. It's the maximum, and it starts. So no more acceleration at that point. Yes, we had a question.
Yeah, from the classical understanding of mass,
yes,
it basically it's a quantity that basically depends on how much matter we have in the particle.
This is effective.
Yes.
The rest mass remains the same. The rest mass, if you would have that one electron out of the lattice or without the field, it's the same. It's called rest mass. But this is for the motion under the electric field in a crystal. Because it is these bands which make it different. It's the bands. So now it's a good moment, I mean, these days, that you kind of play and think different dispersions, what effect it would have on the effective mass. In which cases it will be the strongest, smallest, positive, negative. It's a quick thing to do, it's helpful. All coming from the band structure. Okay. And today we'll continue with the applications. We'll talk about optical properties today. Optical properties. Anyone knows already what it means, optical properties? Let me also write so that you have it written. It's a response to the visible light, to the electromagnetic radiation, specifically visible light. I remember visible light. Check, I think 39700. I'll check. More or less nanometers. It goes from the violet to red. We are talking about energies of, I don't know, it won't correspond exactly, but between 1.8, 2.8 eV. And what can happen? You put your crystal in an experiment and you shine light on it. What can happen?
The electrons will be excited.
Okay. Okay. They are excited because they absorb this light. Okay, that's one scenario. But it can also happen, as we'll discuss today, that the light passes through completely in some cases, or it even reflects. And all this depends on the properties of this crystal. Let me just draw. This is our gray crystal. I put light inside, and it can pass inside. As with, this is intensity I0, with some intensity I0. It can just finish it inside. It can be reflected, or it can first refract inside and then be transmitted. From the conservation of energy, you can also write that the coefficients of reflection, absorption, and transmission is equal to 1. This is old stuff. Now, all of them depend on the properties of the crystal, while absorption depends a bit more on the band structure. And we will try today to describe and characterize the absorption of light by a crystal. Again, I will mostly focus on the electric field. Which has H omega and Kr dependence, which depends on R and T, sorry. And this amplitude describes the I0, the incoming intensity. I mean, these are all things. You did study E&M electromagnetism at some point, all of you. because at some point here we will start discussing, and if you never saw it, it can take a while. Good. So what we want to do is actually take this electric field and this interaction as a perturbation. This is, we want to do something of this time, of this type. This is time dependent, space dependent. We want to just describe how it will interact with our crystal. Now, imagine you have a molecule, I don't know, simple molecule. And I put it in electric field, like in this direction. I know the energy. The energy is equal to dipole moment times the electric field. It can be a line, it can be whatever direction, it can give a torque, well defined, well known. Now we have a crystal, an infinite system. Can I try to describe this as some charge times density times the field, integral over the whole space, and then I have over the whole space integral? It will not converge. This won't work. I don't have a simple way to describe this, as you can have for molecules, for finite systems, not only molecules, for any finite system. So we have to kind of build the formalism for it. We'll do the shortest possible derivation. We have to find a way to describe it. And I will start talking about gauge invariance, because this is a problem, what we have. You heard of it? You don't? Okay, it's nothing smart. From the Maxwell equations, which are gauge invariant, you know that divergence of B is 0. And from there you can write that the B field is rho XA. From the other equation, well, let me just not make a mistake in the, I'm using CGS, sorry. This one doesn't have any C's either. Rho XE is minus dB over dt. And from here I'm writing, let me write the field in my way.
No.
No, it has to be consistent with this. Sorry. Otherwise they have two kinds of symbol for one thing. And this will then be some potential. So this is the first potential I'm introducing. This is the second one. And what was it? Plus the T. And this A this one has a C factor. Sorry. I made a confusion. From here I can write minus 1 over C d over dTA. And A, as you probably know, as the vector potential. And phi is a potential, which are not possible to be observed. So you have a choice to choose them, but they should not change your fields. Although, to confuse you, there is this effect called Aharonov-Bohm effect, which some people interpret as the observation of the vector potential. Others don't agree. I will let you to explain this to me at some point. However, these are not supposed to be observed, A and phi. They don't change the fields. But you can adjust them to make it easier to calculate something. So I can express A also as I can add to A any kind of derivative equals in time and phi can express C, there is a C here. I can choose this function f whatever I want, as long as the vector potential has this form, and you can see it if you put it in this expression, you will see that actually these parts will cancel. This one will come as the time derivative, this one will come as a space derivative, and it will completely cancel. So I have a complete freedom to choose these things. And in what I'll be doing today, somehow it turns out that the best choice is to choose this potential to be 0. And then I can see from here that E should be
Excuse me.
yes, sir.
So this should be applied to both electric field and magnetic field.
Yes.
So
Yes.
shouldn't we define another condition because B also has to be unchanged? So
But it's coming from here, right?
so, yeah,
If
because,
you
del
have,
cross del F should be 0, some condition like that.
it's in already. Here, if you apply,
Okay, sorry.
this
yeah.
gives you
Yeah.
also 0.
Yes.
This is 0. If you have Roth divergence,
Okay, that's a scalar function. Okay, yes.
it gives you 0. It's a bit fast because this is not the main point. I'm just building the formalism, so it's not the main point. Was I going to say? I forgot. I was going to say something. Fine. Here you could also imagine that this should be equal to, that the field should be equal to this. No? And then you would express A as some function of some potential times C times T. If you would imagine that you would get this dependence for A, if you would go. However, this is also called Weyl gauge, temporal gauge also. It's not one of the most commonly used, but it's a useful one. And so let's take what we know. Okay, Maxwell equations are gauge invariant, that you know. The equation is gauge invariant. Dirac equation. So we want to use what we know from Dirac equation to describe our momentum. Right? I'm putting already the negative charge of electron. This form of the momentum is gauge invariant. If you take a normal way, like mr, which is velocity, plus qa, this is not. So this can be shown to be gauge invariant, and that's what we'll be using.
Excuse me, I don't understand the concept of gauge invariance that you're talking about.
That it should not depend on changing the potential. I can put whichever form of the A satisfying these conditions. I have this freedom to choose this F completely, choosing the phi and A. And my equation should not change, because these are not observables, A and phi. They are a way of mathematical construct. We just fit the equations which just make it easier to solve. You cannot observe them, except in this effect that some people claim, but mostly the others don't agree, that you can observe in the flux, Mobile flux, that you can observe the vector potential.
Okay, some people claim that you can observe it.
In the Aharonov-Bohm effect. But I don't think that majority agrees. It's just, I mean, it's good to read and to try to understand.
But what kind of physical sense does it mean? Because we can understand like magnetic field B.
It's mathematics. It's just to help you operate with it.
But when they are measuring something, they should be measuring some physical quantity. Maybe like when we measure magnetic.
Okay, I'm not an expert on Aharonov-Bohm, that you cannot, I'm not going to answer. They just claim that there is no other source, that it has to be the current coming from the A. They see the flux and they claim. Some people, others are explaining it from completely different arguments. I'm just kind of inviting you to read about it. Maybe choose a seminar on that topic. I'm not sure is it on the list, just to understand, and then I come to listen to a seminar. Okay. So this is done. And now we can write this and try to come to the form of the H0 and H prime to see what is the perturbed Hamiltonian. So H is equal. 2mc p times a plus a times p plus e square 2mc square a square plus v of r. Okay, I should write this v of r here. So I can easily single out the H0. Let me just stay linear in A. So I will disregard this as small, and I'm calling this as my perturbation. I'll come back to here. Any questions? So far it's more or less E&M and basic mathematics. So today we'll talk about absorption. It means that the atom gets into excited state and how it happens in an atom. You have levels, no? And in principle, you can excite one of the occupied levels, electrons, to go into unoccupied level. So in the case of atom, because it's deeper than a crystal, I think I took example always of the beryllium, which has 4 electrons. What happens? This is 1s, 2, and 2s2. Second level 2s electron. Okay. You shine light. And you can excite. Have a problem? You can excite electrons to unoccupied levels. We already derived the Fermi's golden rule for the probability of, how did I call it, F, initial to final, as final or initial first, initial. Well, it doesn't matter actually. It's final, and here will be final minus initial. Proportional. But there is one more rule called selection rule, which says when you excite, you can change the quantum number L by 1. So from the S level, I can go to P. From P, I can go to S or D. But from S, I cannot go to D. Okay, so I have two S levels. I can go to the 2P from both of them. But this is the smallest energy, this one here. So if I draw the absorption intensity, the lowest energy to excite something will be from 2S to 2P. So 2S to 2P. Now I don't know the intensity. This I cannot know. It depends on other factors. However, I can just say where it will happen at 2S to 2P. The next one will be 1S to 2P. And then you can go higher and higher. The levels become more and more dense. At some point you get a continuum of levels, because these levels are essentially continuum, empty levels. And then, if you give enough energy, you can take the electron out. Ionization, it's out. This is in the case of an atom. I hope you've seen this before, nothing new. But what happens in a crystal? In a crystal, you have a band structure. Okay. Whatever. I don't always have to put it like a round gamma. I mean, I somehow tend to, but it's not necessary to plot it. And now I don't have any more a given energy to. I can go from here to some other band. Delta L rule still is valid. And you know that each of these bands has a character, no? SP, and so on. So delta L rule is still valid, but I don't really know how to describe transitions here. And this is the goal now, to be able to describe how to absorb a quantum of light in a crystal, by a crystal. So, we start from our field. I'll write it again, what I already had. And our vector potential in the rail gauge gives us, okay, let me write it. Because I deleted the thing. And from here, because the field is 0, potential is 0, this is the expression for the electric field. From here I can derive A as minus Ci omega Okay, maybe it's just to have it consistent with my later notes, I will change the sign here. It's the same thing. I can put this this way, but to have the same, I mean later I have this note, so to keep it the same sign, I'm changing it to this. Okay, so from here I can express the vector potential to give this form. Okay, to everyone. And now let's plug this into this. If I had space for that. To do it, I would like to keep this picture, but maybe not. I'll redraw it. So, our potential okay, furthermore, I was writing the vector potential in a very similar form. Zero. And this is the H prime. And my block states I just write the bend. UK of the N, which then I can expand as a Fourier transform. Okay. And now I'm going to evaluate in the perturbation theory. Initial and final. Well, it can be different and I won't write it. So, what do we have? Very big integral, and maybe better right before the factors. E over m 2mc, and then this part here would come also, minus ci omega 0 E0 amplitude. Okay, and now we come to the real stuff. This will be the K initial. No, in the real space, sorry. K initial R times the sum over these G's. K initial G This is for the first wave function. Then comes the PA part. And the A has this dependence. Times, I have to continue here, times the final wave function, IKF minus I. Now I have to use some other G because it will be independent in the summation. UKF of G prime E minus I G prime R.
EI.
Not minus, right? Good. This is prime. It's a bit lost. It came with the integral. Okay. Now I don't have any intention to solve this integral completely numerically, but what we can see, we want to find a condition when it's non-zero. And this is what I want to find actually. Under which conditions it can happen. I don't want to say with which intensity, but just the conditions. Now we have many periodic functions. So let's put them all together and impose condition for this integral to be non-zero. Now I will have two integrals, two kind of cases. I'll focus on just one of them. It's the same for the other, no? So I will just say there is a factor here where I put all the constants, different terms, and I'm looking here for the exponents, exponential dependence. We put plus I, and then factor out all of these cases. Minus Ki is the first one. Minus Gr. Then plus K. Plus G prime. Times R.
Plus I got
Okay.
KF.
Okay.
Yeah. I completely missed that one. Plus Kf times R. And you remember, you are solving many of these cases when you are expanding potential in a series, that the only way to have non-zero this integral is this guy should give zero. Minus Ki minus G plus K plus Kf plus G prime should give zero. Okay. What is this K?
The electric fields K.
The light. So I can express this. I know the value. This will, lambda is around 10 minus 6 meters. And this is roughly, what, 10 to the 7? Doesn't matter. However, A is, for these guys, 2 pi over A. A is typically 10 minus 9 meters. So G will be much, much larger than K. So, tell me, Joe.
The crystal.
This one? This is the G vector.
10 to the minus 9.
The
Nanometers.
crystal spacing.
8 nanometers.
That is
Angstroms, nanometers.
So it's the same for all every crystal.
Typical value. I'm just saying the difference between the two is at least 100, but more likely like 1,000. So I'm making a case to say, let me just disregard this because it is so much smaller than the others. That was the point of the numbers. And then I can write Ki minus Kf, just shifting to the left, is equal G minus G prime. Oh, G prime minus, yeah, G prime minus G prime. Huh. This is the condition that we got. Relating the incident and the final wave vector with the difference of the G vectors.
This is the same.
The next condition, we always in the first Brillouin zone. So this should be within Brillouin zone. And now I'm asking you, for what values of G prime and G it can happen? Because it is the smallest G, except 0 G, which spans the Brillouin zone, which determines, like in 1D, what you have minus plus pi over A minus pi over A, which is the distance is exactly the first G. So the difference of these two should be within Brillouin zone. How is it possible? In which case is it possible? If I take the first one, G 2 pi over A, and the next one, I'm getting a difference of 2 pi over A. So it means that these guys have to be at the edges, but my initial K can be anything. I don't have to be at the edge to be doing it. Anyway, edges at the same point, so it's not helpful. Let me ask you, what is the condition on G prime? Maybe it is easier way to ask the question. You are free to talk.
Same.
Yeah. The only way. So this has to be 0, which means that G prime has to be equal to G.
Same means like similar distance.
And it means that Ki has to be same.
Yeah, has to be same. It's a vector.
Because it's a vector.
It's a vector.
It's a vector. And it means that Kf has to be equal to Ki. So I will redraw the picture of the bands.
This means no absorption.
I'm asking what it means.
Yeah, because nothing is lost. Ki equals to Kf means same energy. Initial and
No.
Okay.
What does this mean? Means the K is the same. So I want to go from this state. This is Ki.
So like
I want to go
yes,
absorb energy from this point, from this state here. What it says, it doesn't say I cannot absorb.
Okay,
No.
so
It
yeah,
says
change in n is possible, but not in k.
exactly. You can change the level, the band.
Yes, here we have
sorry.
two different indices. Yes.
I can go up, if it's the L, delta L equal plus minus 1, but I cannot change K. So it is called a vertical transition. the only one allowed. Well, then there are exceptions and stuff, but this is the main thing. This is the. Is it okay?
Could you please explain that why G prime minus G zero?
Would I explain again?
That G prime minus G is equal to G.
Okay, I'm saying I put a condition on a difference of the initial and final wave vector. So I will go from Ki to the state with Kf. But I'm using Ki and Kf both in the Brillouin zone, so that difference has to be within a Brillouin zone. And now I'm asking for which G's, and G's are reciprocal lattice vectors. It is possible, but the shortest G actually spans the whole Brillouin zone.
Yes.
And then this is already one of them is too big, which would put a condition that Ki and Kf have to be at the edges of the Brillouin zone. So it doesn't make sense. So it means the only way I can get this to be within Brillouin zone is that their difference is 0. They have to be the same, which means that Ki and Kf have to be the same. So I can go, well, as long as delta L is allowing it, only vertically changing, exciting the states. But you see, it is not so trivial here, because the energy difference in the atom, you knew the levels. And you knew exactly, to go from level 1s to level 2p, I need this much energy. Here, it's K dependent. It is much more complicated to tell. So you will have it just for some K allowed, but not for others.
Excuse me.
Yes?
Previously, while talking about the transition, atomic transition, you mentioned, we all know that delta N should be 1.
Yes.
And you said that this should also happen here.
Yes.
But up until now, we just know one quantum number, that is N. So there are other...
Okay, they also have a nature. That's why it's not introduced so easily in here.
Okay.
The bands, well, I can show you a few band structures.
Yeah, within N, K also changes in energy. Like K is also responsible for change in energy. For example, it moves from
Along the
yeah,
zone, yes,
along
sure.
K. So that is already introducing difference in
Okay.
energy for
But
a particular N.
L won't be so much on the difference in energy.
L actually, yeah.
L, it's the character of the band. It can be also S, P, or D. I mean, the easiest trick, which I tell to my students, is S is usually like parabolic. P also. So if you want to look at the band structure and get a feeling what it might be, S will be usually around gamma, at least this shape or this shape.
So while doing...
Just to get intuitive picture.
So while
Ma'am.
deriving the atomic like solution for an atomic problem, we introduced NL because we wanted some specific quantum numbers to describe our
Yes.
state, because our Hamiltonian was in that
That
sense.
is
So how
always preserved. If you solve band structure by binding, you know what is your atomic wave function. You expand in atomic wave functions. You will have S or P or D, whatever. So it's there. If you do density function, you can also get by the right symmetry. It can recognize what level you have. Is it S or P or D? So it can always be said.
even in quasi-free, like,
Yeah. Quasi-free, it's more, you don't have many D, but it's assumed to be all S and P.
yeah, but obviously in atomic case, like orbital thing was easy to understand because it was already
It's
always
easier,
in the influence
definitely,
of the
definitely. It's easier, but you can always define it. You can always define it. Or by symmetry, or by assumption of the starting wave function. if you expand in S and you get an S in the end, yeah.
Vertical transition is only allowed if the states above are empty.
I cannot understand.
Is the vertical transition only allowed if the states, if the bands above are empty?
Empty, yes, 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 yes. You cannot go to all the field state, obviously. Yeah, this is assumption. What I was drawing was something like this, but actually, yeah, it's maybe a bit confusing. You have to, it has to be empty. Okay? So, if you draw, for this case, an absorption intensity, you see that if you have a semiconductor, let's say, like this, you put the Fermi level here, it won't happen for just any energy or photons. No? You will have, in this case, you will have, starting from some point, this is the smallest one in this picture, the smallest picture. So, and this happens to be the gap energy in this case. And then it will go, so this is like a very dense mesh of different transitions, and in experiment they cannot measure it very dissolved. So then they measure a big blob, and which has some structure depending on the intensity. So, at this point I could introduce, so far you're following, it's okay?
Yeah.
Two cases, two different semiconductors. So, what I drew here is one case, and then there is a different case. Maybe I better copy it. It's a very hard thing to draw it, for me at least. Maybe I don't need this. Let me just draw. These are bands, and the higher band will be. I'm really not good at drawing this, right? I'm drawing it as a metal, sorry. Okay, almost there. Okay, I can also draw this to make sure it's the energy and some k direction. So, Fermi level is somewhere here. Is this a metal or insulator? Or? Okay, it's a semiconductor, but I cannot tell because I put no. But what is different here with respect to this semiconductor or insulator?
Here, like the minimum energy gap is not defined in this case. Because
I mean, the gap is this.
yeah, but we are only allowed like CMP transition, so that is we can't go over slash like.
Okay, so before we go to the case of vertical transitions, let's just first differentiate two kinds of semiconductors. This one will have our insulator. This is called direct gap. And this is called indirect. Let me just write it. Indirect, and then the array vector corresponding to the balance band maximum is different from the wave vector. I took a very long definition corresponding to the conduction band minimum. Yes.
Is it experimentally possible to like modify this indirect gap of semiconductor?
To modify. I'm not aware of it. You know, this is a property which is fixed, and you choose materials for applications for electronics, depending if they are direct or indirect.
Oh, so
Similar.
this
So
is
it's a
still
property.
this is still useful. Like even if something
you
has
have to
happened.
know it. This is a very useful information for electronics. This is, I mean, people who work on it, they can tell you all of them, all of them are direct or indirect, because it depends. It changes the applications that you can do with them. I'll just illustrate one small example, but it's very important. So this is silicon. Oh, it's related, it's not very similar. So what happens if I shine light on silicon? What will be the corresponding absorption spectrum?
I don't like. There must be minimum somewhere.
Because it cannot do this.
Yeah. So maybe that one or.
On my picture, it's very hard to see.
Yeah.
I agree. I cannot tell either, and it changes every year. No, I cannot repeat the same picture. So what will be the smallest? I have no idea. Maybe this. No. So this will be the gap energy, but I don't have anything at the gap energy. Here I was starting at the gap energy. This one here was the smallest. Here at the gap energy, I cannot make any transition. But they start somewhere higher, depending on the exact band structure. And then I have the same complicated. Is it okay? This value, which is the minimum value at which vertical transition can happen, is called optical gap. So I think will be roughly this one in this picture. But and these things are measured very easily. You just plot the absorption spectrum, which is a very direct experiment. So what happens when I excite an electron in this case? If this is the way, I mean, this is, let's say, the optical gap. Let's say, I'm not saying this corresponds to silicon completely, because I think it happens somewhere else in silicon. I just didn't draw it very well. You get a hole here, an electron here. A real material will have scattering present. Scattering is a very fast process. You remember that tau scattering was 10 to the minus 14 seconds. So this electron will end up here. It will go to lowest energy. Also, the hole will move. But then you will have at some point, I don't have a good plot, sorry. At some point, it will be possible that this hole and electron come close together they form an exciton. They recombine. Recombination of electron and hole. So we talk about the exciton. This you will learn much better. And I mean, I'm not even talking about it. I'm just giving a notion now.
Excuse me.
They,
The scattering affect also the holes, just like
Yes.
the electron
Yes.
has
Yes.
so where
Yes.
is the hole?
in the minimum, but on this picture it's not really coinciding with the, so I don't want to plot it because I don't have the two-time structure here. What I have to copy it, but it's really, it has to have the minimum at the right point. It's,
Okay.
and what you will actually get, when they recombine, they will emit energy. And they can emit energy already at the lowest energy difference. So let me, here. Luminescence. Okay, recombination is happening in the time scale of 10 minus 6 to 10 minus 9 seconds. And this can release a photon, with the release of a photon. Messes? So it is possible to emit light at the energy lower, how do they say, than one necessary to excite the system.
Excuse me.
So it will scatter very fast.
So while going from low, like valence to conduction band, we follow Ki equals to Kf.
Yes.
But while going down, this doesn't.
This is
have-
recombination. This is not vertical transition. Just when they happen to be, now my drawing is very bad. Normally you would have here scattering also. Electrons, these guys of the higher, will try to go to lower states. And this thing will come to the top. And then there'll be the smallest energy difference, the electron in the hole. And they can recombine.
So it's
But
a-
this is not a vertical transition, not. It's a different process altogether. And you can actually get a signal, but it's not absorption, it's emitted light. So there are two different things. Here, absorption. This is emission. This light is emitted, not absorbed. At the energy of E gap, for example. At the smallest possible energy. Reynolds? And the last thing for today, we will talk about how light can be absorbed by semiconductors and how color of the crystals, where is it coming from? The short answer is from the gap of the semiconductors. picture. You have a gap. Let me just first write the lights. This is a very rough red, orange. This is the visible spectrum. Yellow, green, blue, violet. So roughly the energy is 1.8 eV, blue 2.7. Well, just roughly the energy is going up in that direction. Just to get a feeling, because we talk about the gaps. Now, let's say the gap is larger than, what is this, 2.8. The gap is 5 eV. What will happen? If the gap of this crystal, of this semiconductor, is 5 eV.
Yes.
Let's assume 5 eV.
It's no longer visible.
No.
It will transmit.
It will transmit. All the light, visible light, will just pass through. Nothing will be absorbed. Let's see the other case. If the gap,
Excuse me, madam, before you do that,
yes,
because you didn't finish for me. It's like the energy of the gap is 5 eV.
Yes.
And the one that is coming has 2.
this is light, visible light.
Yes,
This
yes,
is visible light.
With 2.7, for example.
2.8, I don't have it written,
Yes,
but
yes,
it's
yes.
somewhere there, yeah.
You're saying that now it will just be it will not be absorbed in this case.
It is, if the gap is 5 eV,
Okay.
it is direct gap, let's say,
Yes.
in the case the easiest to observe, direct gap, then it cannot be absorbed.
It's not enough.
You cannot excite any of the occupied levels
Okay.
to go into the empty, because the gap is too large. You're sending energy of this size. And the energy, the light,
Okay.
so nothing can happen. Light passes through, it's transmitted. Do you see how gap is important? And then some people even confuse metals with insulators. Even in this case, there are many nuances with which you have to take into account. Okay. If the gap is smaller than 1.8 eV, so now you have a tiny gap, and the light coming is much larger. So imagine that the light you're coming is this big now, because I don't have units.
Then it will find some other key so that transition can take place.
And all is absorbed. Can you be writing? No light is transmitted. And in this case, the material is called to be opaque. Opaque, I'm not sure. I'm not a native speaker, so I can hear everything.
I think none of us are. I think none of us are. Maybe some.
None. Yes, it's true.
Yeah,
Some countries have English as official, second official language, but none of you, no? Well, some parts of Ghana, they have it. Are you from those parts? I see. Also, it's the property of being opaque is that it's not transmitting any light. So it's enough if light is reflected, as in the case of metals, which do not have any gap, but they reflect light, and they're also opaque. But now we are differentiating semiconductors. So the ones which have a small gap will be opaque. But now I'm asking you, what if the gap is in the center of this, in the middle of this? Let's say 2 EV.
Then 1.8 to 2 EV will be absorbed, other will be transmitted.
Yes.
Dispersion.
Do you agree with that?
Yes, I agree.
Shall we now be able to see the colors?
Exactly.
Yeah.
Exactly.
Okay.
And the point is that you will see the color. So you will absorb, let's say, these. And these guys will pass. And you will see the color which is not absorbed, which can transmit. So you won't have anymore the full spectrum, you'll have just, let's say, blue-green. And this works for many cases. But then they add some dopants or something which changes color of the material. So it's not always so easy to spot it. But this holds in many cases. So now you know why some materials have blue color. And you can actually see it and you can guess its band gap. Huh? It's like a magician. Any questions?
I just need a clarification.
Yes.
Now, for example, if we see blue color, does it mean that basically it has transmitted from red to green?
Absorbed. These are the smaller ones.
Yes, sorry, it has absorbed from red to green, and so now it's showing blue.
Because the blue is being transmitted.
And then what happens to the violet?
All of them are being, this is the threshold. This is larger. I'm just putting the number now. I don't know exactly, but all of these can be transmitted. So bluish color.
So
it's not a singular color.
So it means that I can see. Then how do we judge that it is exactly blue? I mean, what happens to the violet that has also been transmitted?
Well, you will see a mixture of blue and violet, let's say.
Wow. Then when it starts from maybe yellow, what mixture will I see now?
Well, also it depends a bit on the band structure. You might happen that you don't absorb all the frequencies equally.
Okay.
It depends, because this is just a general thing.
Okay.
Now, if this one is the wrong, if it's not SP, if it's some other band, you can have a problem absorbing everything, so the next one will be too high. There are nuances, no? It's not, but it works. This is the first tool you should learn.
Okay.
Then you can add some dopants, impurities, which will act as absorbers or not. We change the property. But roughly, this is true. Any other questions? I see Joe is very concerned to finish the class. Checking the time. No, okay. Any questions on this? Or we can solve, if you want, we can solve a problem from before. So this is finishing now the applications of band theory. On Thursday you will talk about something you need to know, Born-Oppenheimer approximation. You will go back to atoms. From electrons you go back to atoms, ions essentially, which we neglected until now. And then it will continue from the next week with phonons. Yeah. And that's it. In terms of lectures, that's it. So we have
We are not doing magnetism this.
No, I'm very sorry that you guys this year won't learn any magnetism. I was quite surprised. I was getting diploma students for the thesis, and I would talk about basic things in magnetism. Never heard of it. Yeah, that's pity. That's really pity because it's important, and somehow no course is covering it. Yeah. You have a question?
Question. Imagine a case where all the electrons have been vertically vertically transmitted to the next band. Then all of them in the valence band,
All of them will be transmitted, you're saying?
Yeah, is it possible?
No.
No.
No,
Maybe my
it's-
question stops there.
No. You would invert completely the population, no. Well, also when you excite, you will have very fast de-excitation usually. There is a process of relaxation. Now, it depends on the time scales which happens faster. But you won't ever have, inverted full band up. That's not happening. Tell me, you want to solve something?
Yes.
Or you are happy to go? You have at 11 something?
No,
Not today.
the
No.
lecture has been shifted, I
You want to solve the problem which you mentioned yesterday,
think.
to guess the structure from the dispersion relation. It's this one, yeah. So you have to guess, not guess, you have to find the Bravell lattice and even the type of orbitals. You solved it?
I'm not sure.
Rabindra, you had time to solve it?
I was busy making slides for time.
Oh. Yeah, I would really like to listen to all of you. It's quite fun, actually. Everyone always learns something. And you can choose a topic which you're really interested in. You can learn quite a bit. I mean, when you only have to put energy and time in it, can be even useful.
December is going to be a little bit more hectic because then we have 2 exams, one on 4th of December, another one on 12th. And maybe I'll have my second round of presentation around 12. So
Okay. Well, not every presentation has to be perfect. I mean, you do your best, but you have 5 presentations?
generally it should go up to 5 rounds, but depending upon time and other factors.
Yeah,
maybe
okay.
4
When I was, we had 5. And well, it's okay not to have one. If you're always good and one you didn't prepare that well, but you understood basics but it wasn't well prepared, it's okay.
Because the first presentation I think is always the easier one because everything is ready.
I know. But you're also more shy and for the first one it's a bit, first time you are getting up on the camera.
Yeah, on the camera.
Yes. I don't want to think, actually I should turn it off now.